Hi, my name is Olivia Gehrke, and I'm a rising senior at Oregon State University studying mechanical engineering. This summer, the projects that I focused on were given the overarching title of Intelligent Fruit Picking with In-Hand Sensing. My project mentors were Dr. Joe Davidson, Miranda Kravitz, and Alejo Velasquez at Oregon State University's Intelligent Machines and Materials Lab. Now, Washington produces over two-thirds of the apples for the United States, according to a 2021 polling done by the USDA. This means that Washington controls the apple market and the prices, which makes their success key to the stability of this market. Despite being the largest producer of apples in the United States, the labor shortages in these orchards have resulted in higher harvesting costs for farmers. This is partially due to Washington's reliance on the H-2A guest worker program to meet the harvesting needs of their orchards. The H-2A program has a set minimum wage value that is higher than the minimum wage in the state. This means that profit margins for the farmers get even tighter every year as this minimum wage value increases. Now, robotic arms are being studied as a way to reduce these worker costs by replacing human workers with autonomous robots. The problem is that robotic arms currently struggle with picking success rate, with a recent study finding them about 62.8% successful in terms of picking apples. This reduced success rate can be due to perception error or clutter like leaves and branches that lead to incorrect gripper placement. This reduced picking success rate is what is currently limiting commercial adoption by farmers. Now, as a way to increase the success rate of these robotic arms, my two projects this summer focused on creating a classifier to analyze and classify when an apple pick was a failure or a success, and creating code to rotate the gripper such that all three suction cups on the gripper pictured below are engaged. The first project I will go over is the picking classifier. Now, the goal of this classifier was to use the force data and the pressure data to classify if the pick was a failure or a success and state the time that it took for the classification to occur. The goal of this classification is twofold. The first is that the classifications can be logged such that the farmer can go back and re-pick the failure so that no apples are missed. The second goal is that the picking motion can be stopped faster than a hard-coded value, which would decrease the picking time. Now, this diagram showcases what the apple experiences before and during the picking motion. The stem of the apple is treated as a spring due to the behavior of apple stems, which means that it can be represented as a spring problem. As the apple is picked, a force that counteracts the force of pulling the apple will occur in the opposite direction of this movement. This is the force that will be used in the heuristic. Now, the code has two parts to it. The first part is that the code moves the index to wherever the force first passes 8 newtons. This ensures that the heuristic won't trigger too early at noisy force data. The second part of is the heuristic used for classification. It is important to note that the derivative of the force versus displacement data was utilized as a measure to decrease the noise of the data so that the analysis could be smoother. The two criteria that need to be met for the pick to be a success is that the derivative was below negative 0.1 and that the normalized pressure value was below 800 hectopascal. If the pressure was below that value, then more than likely 2 or more suction cups would be engaged, as the engaged suction cups have a much lower pressure reading. Now, this slide is showing two graphical results, a success and a failure, and a video of a real-life successful or failure pick next to it. The top graph is a successful graph, which is shown by the way that the force sharply decreases as the stem is released from the branch. The classification point is represented by the red line, which coincides with a sharp drop-off in force. The bottom graph is a failure graph, which is shown by the way that the force slowly decreases to about 0 as the fingers of the gripper slip off the apple. The red line is showing at which point the heuristic labeled the pick as a failure. There is a bit of a delay, but that is mostly just due to how the heuristic is designed. Now, this diagram is the confusion matrix of the classifier being tested on a 2023 dataset from Prosser apple picks. Now, the dataset is smaller, with only 17 total picks that were viable for being tested due to the pressure data not being recorded with every single test. Despite the smaller sample size, the results do appear to be promising, with a correct classification rate of about 82%. This is even higher than the success rate was when the pressure wasn't included in the classifier. Now, the work that still remains with this classifier would be to do proxy testing in the farm and the lab. This would allow for a larger sample size to be tested, and the classifier can be tested on different picking motions in a controlled environment. Once the proxy trials are completed, a field test should be done so that the classifier can be tested in more real conditions than ideal conditions. The second project is gripper adjustments using pressure differences. Now, the specific gripper used here at Oregon State University has 3 suction cups in a triangular shape that suction to the base of the apple so that the apple doesn't move when the fingers come out to pick it. The more suction cups engaged, the higher the likelihood of a successful pick. Now, usually only 2 suction cups are engaged, which can be seen in the diagram below. Now, the project is working to rotate the gripper such that all 3 suction cups are engaged before picking to increase the pick success rate. The code for rotating the gripper has three components. The first component assumes that each suction cup is represented as a unit vector, like what is seen in the diagram, which is then multiplied by the pressure value at this point to add weight to each vector. When these vectors are summed together and the angle from the positive x-axis is found, this is the angle that the robot will rotate. Then the speed is calculated using a correction value that changes the pressure value to a speed value of degrees per second. The third part is an error function that checks that all pressure values are below 400 hectopascal and within 5% of each other. If all criteria are met, then the arm stops rotating. Now, here is a video of some proxy testing being done with this code. As you can see here, all three suction cups do end up engaging after the gripper is rotated. And then once the suction cups are released, the apple drops, which is why my hand is catching it at that time. Now, due to the timing of this project in relation to when the presentation is taking place, not all testing is completed at this current moment, hence why there isn't a results section. The work that is currently being conducted is simple orientation proxy testing. After testing that each orientation of the apple moves the gripper as expected, then the proxy test will move to suspended apples with stiffness that can be decreased as the arm movement becomes smoother. Once these are done, field testing can begin. This would allow for the code to be tested in a realistic setting where each apple will behave very differently. Now, thank you for your time, and here are all the references that I used during this presentation.